Very happy to be here. How are you all feeling? Very good. It's a pleasure to be here, especially since I'm going to be speaking about a very exotic subject, which you might not immediately get very excited about. It's so far away from what we usually think about. And my plan for this evening is to tell you all the things we do know about the origin of our universe, the properties of our universe, and why they are so special. And in particular, also what we do not know, and we would like to find out. That's, of course, my job as a theoretical physicist, cosmologist, to find out new things. It's about what we do not know. And to get started in this journey for this evening, let me first tell you a little bit about my motivation for doing the stuff that I do. Now, so I'm going to keep this very simple. So the motivation for my research is the same as this famous person. I just want to understand the origin of our universe, where it comes from, what its properties are, why it is as it is, for no particular other reason than curiosity. Okay? I'm not going to solve the energy crisis. I'm not going to solve sustainability issues. I'm not going to revolutionize medicine. I just made a profession out of being terribly curious. Maybe you remember when you were young and you didn't have all these responsibilities and you grew up and suddenly everybody tells you to be mature. Maybe you remember that when you were young, you were just fooling around, trying out things, playing around with ideas, testing the world around you, just for the fun of it, instead of, making a living or something else. I turned this into a profession. So that's what I'm doing. I'm just going to be, and I will be, and I am, and I was very curious. And I want to know what happened. What happened to our universe? What are its properties and how did it get started? Now, initially, at the turn of the 19th century, or before, I would say 15, asking questions about the universe as a whole was a philosopher's job. It was not really science. That all changed when there was this certain fellow called Albert Einstein who figured out what gravity was. And by figuring out what gravity was, it suddenly became possible to study the universe as a whole. So before I get started to tell you about the special properties of the universe, let me first tell you a little bit about what gravity really is. So what is gravity? Good. So gravity is a very special force. It's not an ordinary force. Gravity is completely and utterly democratic. All things fall in exactly the same way. This is not how other forces work. The only thing that matters, if you want to measure a force, are relative accelerations. That's how you measure a force. But because everything, the gravitational force acts on all matter, all energy, in exactly the same way, everything falls in exactly the same way in vacuum. So if you drop a 100-kilo bullet or a feather in vacuum, they will all fall in the same way. And that means that if you're floating around in space, like these two persons over there, you feel nothing. You feel you're weightless, okay? And the only thing that makes a difference, that's how we detect gravity, are the differences between different locations in space. If there are differences, if you go from one place to the other, then you will see separation of these two astronauts, and that you can measure. And that's what gravity is all about, and it acts in the same way for all matter and energy. And because it acts in the same way for all matter and energy, for all particles, it's actually very convenient, efficient, and correct, I would say, to describe it by geometry. Because what's geometry? Geometry is the stage in which everything happens. Okay? This stage is also a place where things happen. And space and time, that corresponds to the stage where all of physics happens. Okay? And if everything falls in exactly the same way in gravity, you can describe it by geometry. Once you fix the geometry, everything moves along shortest paths. In flat space, on a piece of paper, that's a straight line. On a curved space, like a surface of a sphere, it's an arc. Okay? But all particles, independent of their properties, will follow the same trajectory. And that's why you can describe it by geometry. So this was very succinctly summarized by John Wheeler, a famous theoretical physicist, who basically said, space-time tells matter how to move, which trajectories to follow, and matter tells space-time how to curve. So if you have a very heavy object, it will bend and stretch space and time in such a way that small particles that move around it follow the shortest trajectories in this curved, stretched and bent geometry. Now, typically what people do, they show you some trampoline and balls flowing around, but I think there are better ways to show or to get a feeling for what this means. And the first example, I guess, is this famous example of what it would look like if you could see a black hole. If you would come face to face with a black hole, what you would see is that light rays are bent around the black hole. So you get this very nice, interesting picture of light rays that do no longer follow straight lines, but are curved around the black hole from all different angles. And there is actually an even nicer picture that I want to show you that essentially makes the same point. Oops. Backwards is forward. Yeah. Actually, in the laws of physics, backwards and forwards doesn't matter. It's the same. We could also try this out, but I think that's probably not going to happen. Yeah, right. Sorry. You might think this is a joke, but it wasn't. So here you see another example of exactly that phenomenon. So space and time are curved because of the presence of a large amounts of concentrated matter. So that also means that you can actually determine the amount of energy, the amount of matter, the amount of mass, by looking carefully how light rays are deflected. Now this is an example, and you should not care about these pointy stars in this picture. Those are nearby stars. You should ignore them completely. The other stuff in this picture that is of real interesting value are these stretched blurbs out there, which are all galaxies. They're far, far away galaxies, and their light that traveled towards us for millions, maybe even hundreds of millions of years, is actually being bent around, curved and stretched around by a huge body of matter that the light rays are passing in their when they are going towards us. And these are known as Einstein rings. So apparently there's a concentrated source of matter which apparently is invisible, which we cannot see, which disturbs these light rays in such a way that all these galaxies look like stretched out. Okay? So it's like a lens. It's called a gravitational lens. And that's essentially what curved space-time does. And the bottom line is, which is also important for all the other stuff that I'm going to say, is that if you can trace this geometry, this stretching and bending of space, you know how much matter is there. You can do the computations using Einstein equations. You can actually compute how much matter is there. So once you know the geometry, you know the amount of matter, and vice versa. If you know the amount of matter, you know the geometry. And that's a very important realization to be able to do cosmology. Now, I was told that you should never show an equation. So if people are now fleeing the exits, I'm sorry. This is, but I wanted to show this because this is one of the, I would personally consider this one of the highlights of science in general, physics in particular, and especially theoretical physics. These are Einstein's equations. Let's not dwell too much about what they mean. The Latin symbols R and lambda and G are certain, they call them tensors, but they are matrices. They have all these different independent components, and the different components are labeled by these Greek indices, which run from 1 to 4. Okay, so they're big matrices, and the only thing you need to know is that this side, so it's a very summarized and nice mathematical formal equation, and the left-hand side all represents geometry. It's about geometry. It's about describing four-dimensional space and time geometry. The right-hand side is also a big matrix of stuff that represents matter. Okay? So in the end, what this equation tells you is that the geometry of the universe equals the matter and the radiation in the universe. Okay? That's the most important message, I think, of the whole evening. But that's what this equation tells you, and it allowed, and Einstein realized this immediately, it allowed us to scientifically think about cosmology, the evolution of the universe as a whole, because what we were then already trying to do was to actually trace all the matter in the universe. You know, where are the stars, where are the galaxies? But if you know where all the matter in the universe is, then this equation tells you that you know the geometry of the universe. And the geometry of the universe is the geometry of space and time, so it also includes time, so it also tells you about the dynamics of the universe. Okay? So Einstein realized, okay, we can now, for the first time, do actual cosmology and try to figure out what our universe is, what its properties are, and how it got started. Okay. You should now be really excited. Good. Let's see if I can get this right this time. Yes. So, as I told you, people in the early 19th century or 20th century were already, trying to see where all the matter in the universe was by measuring the positions of stars and galaxies. And one of the most important realizations that I need to stress before you can understand cosmology is that everything we see, because the speed of light is finite and constant, everything we see is in the past. This is, of course, the dream of every historian, right? We see the past. So, in fact, if you look at the sun, we see the sun as it was 8 minutes ago. If you go to the nearest stars years ago, that's why it's called a light year. Light years is the smallest distance that we can see neighboring stars. If you go and look at our own galaxy, which is 100,000 light years across, so all the stars we see in the sky are part of the Milky Way galaxy. It's, the stars that are at the boundary of this galaxy, the Milky Way galaxy, are roughly 100,000 light years away. So we see that star as if it was 100,000 years ago. And if you then go out of our Milky Way galaxy, the nearest galaxy to us is Andromeda. You've probably heard about Andromeda, and if it's a really clear sky, so you better go out of the country. If it's a really clear sky, this is about the size of the moon. You can actually see this galaxy with your naked eye. But that's millions of light years away. So we see the Andromeda galaxy as it was 1 million years ago. And that's the nearest galaxy. So that's why I plotted this picture. This is a slice of the universe where we measured more or less all the galaxies. All the little dots here are galaxies. And we put them in this diagram so you can get an impression of the structure, of the distribution of galaxies in our universe. So you should also by now be very impressed how big the universe is. It's huge, right? The galaxy itself, our galaxy has 100 million stars. The number of galaxies that we've observed is in the same range. And we can actually probe the distribution. We can more or less see where they are in a three-dimensional grid. And one of the most striking consequences of those measurements, in the spirit of Copernicus, is that we do not live in a special place. It's a vast universe without a special place. Every place looks like any other place. On average, we're average. Okay? So the sun, the Milky Way, it's all average. There is no special place in our universe. It all looks the same. Keep that in mind. So we see the past, and there's no special place. So, having seen the distribution of all that matter in our universe, what does that mean for the properties of our universe? What else, besides the structure and distribution of all this different matter, can we actually see? Can we measure? Well, there's one other thing that we can measure, which is actually surprising. But what we can measure is that if you look at galaxies, so this picture, I should tell you, this is the first measurement of that particular kind. It measured a couple of nearby galaxies. Hubble was the one who tried to do that. Hubble in the 1920s, 1925, a little bit later, tried to measure the distance of these galaxies, but at the same time, he was also trying to measure the recession speed of these galaxies. And he could measure that by looking at the spectrum. And if spectral lines change, then you can determine, just like, it's a Doppler effect. If an ambulance passes, let's hope that doesn't happen. If it moves away from you, it's a different pitch than when it comes towards you. So in some sense, you're just measuring the pitch of these galaxies. And what you find is that the further away a galaxy is, the faster it recedes away from us. Now, this is called Hubble's law, but I don't know how many critical people there are in this audience, but if you look at this diagram and these data points, it could have better been called Hubble's hunch. Because I'm not very impressed by this data. He draw a straight line, but I don't know. It's not so impressive. So this is, just to make sure that we're all on the same page, and it is, in fact, Hubble's law. This is a more modern diagram where the Hubble galaxies are just in this little tiny itchy-bitchy over here, and then you extend it to larger distances, and you'll see a clear linear trend. Okay? Now, this means, if you then apply the reasoning of Einstein, that gravity is geometry, and you plug this into Einstein equations, this means this can be explained if there's no special place in the universe, and you have to have this property that actually further away galaxies are receding from us faster. That means that space is expanding in time. That's the only way to explain this data. And I'll say a little bit more about that on the next slide. So by measuring the velocity and the distance, we now suddenly realize that the universe is expanding, and therefore time had a beginning. That's boom, right? That's really amazing. Time had a beginning, That also means that the observable universe is finite, because if there's a finite amount of time for light to travel, you can only reach a certain distance because of the finiteness of the speed of light. So the part of the universe that we can see is finite. Now, by now, and that's why this plot is over here, by now we can do a lot more careful measurements to determine exactly how fast the universe is expanding. So we look at standard candles, we look at redshift, and then we try to fit models, how fast is everything expanding, and then you get plots like this. This is just to impress you. Okay? So what does it mean for the universe to expand? Because I always get questions about this, right? And I think the best way to explain it is just that if there's no special place in the universe, so people, when you talk about expansion of space, people tend to say, well, there must be a center. Because if everything collapses, then there's a center. No, there is no center. Imagine, so expansion of space is like zooming in and zooming out. In particular, if you're talking about expansion of space, you're zooming in, like we do here, right? We zoom in. Now, if you have an infinite surface, and for all we know, our universe could be an infinite three-dimensional space. So now we do an example with a two-dimensional universe. We have an infinite surface. And if you just zoom in, so you start from an infinite surface, which is the same everywhere, with the same distribution of galaxies everywhere. And now you just zoom in, there will not suddenly be a center. You're just zooming in. So you could pick any initial starting point in this infinite huge two-dimensional surface, and you can zoom in. There is no center. All places are equal in the universe. As far as we know, all places are equal. And another thing that you should see in this picture, so just zooming in, another thing that you should see in this picture is that light, as the universe expands, is being stretched from blue to red. Wavelengths are getting longer, okay? And the reason why further away galaxies, actually, if the distance between these two galaxies is bigger, there's more space in between. If there's more space in between that's expanding, then the relative velocities will be bigger. And that's why you get this Hubble curve, this Hubble law. Okay? The bigger amount of space between two galaxies, the faster their recession speed will be because there's simply more space in between. And that's why you get Hubble's law. So now we suddenly have to deal with a universe that is expanding and finite in size in an observational sense. Okay, so what does that mean? What other consequences will this have? Well, if we zoom in, then basically what happens, temperatures will rise. If you make the densities bigger by going back in time, densities will become bigger, temperature will become bigger, stars can no longer exist. In the end, what you're dealing with, if you go far enough back in time, the only thing that you're left with is protons, neutrons, electrons, and radiation. Now you can go further back and you'll have quarks, but let's stick with neutrons, protons, electrons, and radiation. So in the very early universe, it was so hot, so let's say 13 billion years ago. That's not a number that I just draw from my head, but that will become clear later. So let's go back 13 billion years ago, roughly speaking. You'll only have neutrons, protons, electrons, and radiation. Lots of it. But because it's so hot, these neutrons and protons and electrons, they will not sit together and make atoms. Atoms have a nucleus and an electron around it, right? And they're neutral. This is a charged plasma. And as you then run the movie forward and the universe expands, then it becomes cooler. And suddenly atoms can form. Now I should tell you that when you're in this hot, charged plasma, so there's electrons and protons that are charged particles, photons will just scatter off these charged particles. So that's actually what photons are. They like to scatter off charged particles. So if you take a charged particle and you wiggle it, then you get radiation. So whenever you have charged particles, the light, the radiation, is locked up in it. So it was a very misty affair. You couldn't see anything. It's like driving through a humid cloud, right? So it's in misty. You don't see anything. But then you run the movie forward, gets colder, first atoms suddenly form. And we can actually do these calculations. We can compute how much helium and how much hydrogen form in these very early phases. Those are the main elements that form. The universe consists mainly out of hydrogen and helium, and we can compute their fractions by doing these calculations. And lo and behold, these fractions agree with what we see. Even more so, when these first atoms form, the light that was locked up in this misty phase can now suddenly travel freely. And it does, and it has, and it ends up at the Earth. We still measure this radiation. So initially, this radiation was very hot, but because of the expansion of the universe, it became very cold. And people could have, they computed this, and they predicted somewhere around 543 Kelvin. The radiation, the afterglow of this hot phase, the hot Big Bang afterglow, should be somewhere around 5 Kelvin. And they started looking for it. Well, actually, they didn't start looking for it because they forgot to look for it, and somebody by accident measured this. This is how you can win a Nobel Prize. Don't worry, you can still be lucky. So that's known as the cosmic microwave background. It's like millimeters, centimeters wavelength, and we can still measure it. Ah, thirsty. Ooh, good. Nice. Where was I? So we can measure this, and this is what it looks like. It's amazing. So what you see in this picture, every point in this picture is a direction in the sky. That direction, that direction. And we measure hot radiation in every direction. It's not so hot, it's actually cold. It's 3 Kelvin, 2.725 Kelvin to be precise. In every direction in the sky, which we now plotted on this screen, you measure radiation with a temperature of 2.725 Kelvin. Now you might wonder why there are all these color differences in here. They're exaggerated. So in every direction in the sky, it's on average 2.725 Kelvin, but every now and then, if you look in a slightly different direction, it's 2.72501 Kelvin. And in another direction, it's 2.72502 Kelvin. So there are very, very, very tiny differences that have been exaggerated. Red is a bit hotter, blue is a bit colder. But it's extremely homogeneous. It's extremely uniform. So every direction in the sky looks exactly the same. And it's the best evidence that we have, for something that I already said, that the universe has no special place. It looks the same in every direction. And this is the best evidence we have. This is, of course, the best evidence also we have that there was this hot phase in the very early universe, because otherwise there would not be an afterglow. This is like a baby picture of a universe. So the little structures that you see in here actually grew under the influence of gravity to become the structure of galaxies that we see around us in the sky. This happened, so this baby picture is about 13 billion years ago. 13.4, maybe something like that. Let's not be too overly precise. Give or take 100 million years, who cares? So it's a very old picture, and from this we can actually learn a lot about the properties of our universe. So the next step is to tell you a little bit why our universe is so special. Oh, by the way, I should tell you something. When first, this is the Planck data, and when it was brought to Stephen Hawking, he said, in his own witty way, he said, it was a bit, mischievous, so every now and then, he said, I can see my initials. God put my initials in this data set. You can actually find any initials that you want, but it's a funny joke. He was very happy with this data because he worked on early cosmology, Big Bang cosmology for a very long time, and this is the best evidence that we have. Now, Okay, I want to summarize. And the best way to summarize is to show you a movie. I told you that we looked at the distribution of galaxies that you see in front of you now. So what I'm showing you here in this movie are actual galaxies, and we can move through them in a 3D simulation. And we go further and further away. We go to larger and larger distances. And I want to show you the size of the observable universe. So as you move further out, light becomes redder, as you can see a little bit. We haven't shown all galaxies, but certain parts in the sky are a bit hard to measure, so that's why you see these special places. But if you then go further and further out, the oldest light that we can see, and we cannot see further, it's like seeing at basically the clouds, we cannot see further. We cannot see through this phase of hot charged plasma. So this is, at the boundary, you'll see the CMB, the cosmic microwave photons that we actually still detect. But that's how far we can see. This is our observable universe. It's a sphere. We cannot see any further. And in the middle, you see the Earth, and around it is this structure, large-scale structure of galaxies. And at the boundary is the cosmic microwave background, the afterglow of the Big Bang. This is what our universe looks like. You should again be very impressed. Yeah. So here I showed you again our observable universe, this football with the CMB. You can actually get this as a beach ball. Here you see the CMB. And I told you already that there are small, tiny fluctuations in the temperature of these photons, of this radiation. And in fact, you can show that these small, tiny fluctuations represent small differences in density from place to place, which have grown out, which have become the structure of galaxies. So in some sense, evolution, this is a bit like cosmic archaeology. So you dig, you go to further and further distances, you find the boundary, there you see some fossils lying around, very tiny structures, and then you can predict from these very tiny structures how they evolved to give you this structure, this distribution of galaxies that we see closer to us. Okay? So it's all consistent. So here's a picture of this large-scale structure of galaxies in a box. So we see the primordial seeds of structure also in this afterglow of the cosmic microwave background. So now it's time to tell you what's so special about the universe. And it's useful to have this picture in mind of an observable universe that is this sphere. Now, on this sphere, in different directions, that's the furthest we can see. And we see the same temperature in all these different directions. Now, as you can probably imagine, these locations where we measure these temperatures, because we go so far back in times, they're incredibly separated. The distance between these regions is huge. But the time when our universe began is very close to this boundary that we see. So this region is very far removed from this region, but they still have the same temperature. That's very strange. So I'll give you the coffee example. So here there are many cups of coffee. If I give you a thermometer and you measure all the temperatures in all these cups of coffee, and they all read the same temperature, what would your conclusion be? Shout. They come from the same source, right? From the same coffee pot. They must be poured from the same coffee pot. What do you need to actually, pour coffee in all these coffee pots? You need time. You need a bit of time to fill all these cups. There was no time in this universe, in this observable universe, which had a beginning very close to this boundary. There was no time to communicate between this region and that region, or that region and that region. In fact, it's about 1 degree in the sky, the size of the moon. All these regions in the CMB did never have any time to communicate to each other. if they never had time to communicate with each other, and remember, the fastest that you can communicate is through the speed of light. So if all these different regions are so separate, how come they all have the same temperature? It's a very special initial condition. So the observable universe is inexplicably uniform. The fact that the temperature is the same everywhere is completely unexplained. We don't understand in the standard picture of the hot Big Bang. Oops. Yeah, there it is. I'll just take a sip of my drink, why not? So I hope that's clear. So in the standard picture of cosmology, of the hot Big Bang cosmology, there's no way to explain that the temperature of the CMB in that direction is the same as the temperature of the CMB in that direction. It's inexplicably uniform. Okay, great. What else? The universe, I told you, if we know all the matter in the universe, if we know how the dynamics, how the universe evolves, then we can also determine its geometry. So if you know the matter and how it is, dynamically evolving, then we can also, using Einstein equations, we can understand its geometry, its spatial geometry. And in fact, that's what this data can tell us. The CMB data tells us that if you look at the average distance between a cold and a hot spot, the angular distance in the sky gives you a direct handle on the geometry of the universe. And since there's no special place, this geometry can only be of three types. It can either be positively curved, like a sphere, two-dimensional. That's a two-dimensional surface that's positively curved. It can either be a saddle, it's negatively curved, so a two-dimensional surface that is negatively curved is a saddle, or it can be flat, like a piece of paper infinitely extended in all directions. So because of this data, and we can measure the average distance between a red and a blue spot, we actually know that our universe is flat, which comes, if you plot we call this the correlations, temperature correlations, then this corresponds to this maximum. This maximum tells you what the average distance is between a red and a blue spot. So that's at 1 degree. Okay? And it tells you that the universe is flat. Now that's great. It's amazing. But Einstein's equations tell us that that's absurd. Because a flat universe is an unstable equilibrium. It will very quickly evolve to either a positively or a negatively curved universe. If we measure the universe today as being extremely flat, then it should be ridiculously flat in the past, exponentially flat in the past. A very special initial condition. So that's the same specialness that I was referring to already, according to the uniformness. The temperature is the same all over the surface. It's also a very special initial condition. And being flat, having a flat spatial geometry, is also a very special initial condition. So, faced with these dilemmas, there was a small group of people in the 80s, Alan Guth, Andrei Linde, Starobinsky, Mukhanov, who figured out how to solve all of this in one sweep. And they called it cosmic inflation. So what is cosmic inflation? Inflation suggests that in a very early universe, there was an exponentially fast, accelerated growth spurt. So under the influence of ordinary matter, like we know, particles, stuff that we see in accelerators that we see around us, expansion will decelerate. It's like gravity wants to stop the expansion. But if you have special stuff, exotic matter, and we know exactly because we can put that in the equations of Einstein that I showed you, then you can get accelerated expansion, fast, exponential expansion. And if you have a phase, a very early primordial phase of accelerated expansion, what happens is, there's all kinds of interesting things that are happening, but what it means is that you have to do really exotic stuff. So what I'm talking about is that you grow the universe by a factor 10 to the power 30 in less than 10 to the minus 30 seconds. So it's really extreme. That's why we like it, of course. But if you do that, then our observable universe, the stuff that we can actually have access to, is only a very, very, very tiny part of a much bigger universe. And the reason that this tiny part is flat is the same reason your street in Amsterdam looks flat, according to if you compare it to the size of the Earth. We only see a very small piece of it, okay? So that's one problem solved. The other problem that is solved, because we now have a common origin. This piece has a common origin in this early phase over here that's just very quickly exponentially fast expanding. So it has a common origin. The rules that we previously mentioned about the fact that there was no time to connect these different regions no longer apply if you have a phase of accelerated expansion. So if you assume a phase of accelerated expansion, you can explain why this has the same temperature. It also explains why it's so uniform, why there's all ripples. So for example, if you have some original ripples over here, this expansion is just going to stretch out all ripples. So you end up with a universe that's very smooth and has a common origin and is flat, which is exactly what the doctor ordered. Okay? So, yes. So you get, if you assume that there was this primordial phase of accelerated expansion, you get a oh, by the way, that's another thing that's quite nice, because you could have asked the question, and nobody did. Why is the universe expanding in the first place? And inflation, if you know how to solve the problem of what causes this accelerated phase, then gives the answer. You introduce some exotic stuff that in some sense, gives you exponential expansion and explains why the universe has been expanding ever since. So it gives you an expanding, smooth, flat universe, but there should also be tiny fluctuations. Does it also solve that problem? Because without tiny fluctuations, if the universe is too flat, we wouldn't sit here. You need tiny fluctuations in order to generate structure, galaxies, stars, and ultimately planets to make sure that we can live, that we can be here this evening. So you also need tiny fluctuations. Well, let's first, I'll discuss that in a minute, but let's first understand how you can actually create an inflationary universe. So you need some exotic stuff. What exotic stuff do you need? What you need is an inflaton field. That's a difficult word, but what it means is that in every location in space, the inflaton field has a particular value. And at this particular value of the inflaton field, think about this surface, it gives the universe a particular amount of energy. So every volume of the universe has a fixed, almost constant amount of energy. And if you put that in Einstein's equations, then you get accelerated expansion. It's a miracle. It works. And what you see here in this picture, this is how inflation, that in this model, inflation only lasts for a finite period. So this ball over here, that's basically the value of this field. So this is a particular value above 0. This ball represents this value. And if you introduce a hill, or a potential, as you say technically, then this ball can roll down, and as it reaches this corner over here, it falls down. That's when inflation ends. And when inflation ends, it releases all this energy that was built up in all these space-time volumes, it releases it into the standard model particles that we all know and love, and it produces a hot Big Bang. It's amazing. It's beautiful. So this is how you create an inflationary universe. You need an inflaton field at almost constant energy density, and then the slow roll decay ends with producing standard model particles in a hot Big Bang. Problem solved. Okay? Done. It's almost time also. It gets even better. So I haven't told you how to solve the problem of these tiny fluctuations, but I told you that if you have ripples, before you start this accelerating phase, if you have ripples, they will all be stretched out. So you will be left with a completely homogeneous universe. But that forgets about quantum mechanics. And quantum mechanics tells us that everything always fluctuates. And if you play this game in this phase of accelerated expansion, miraculously and very surprisingly, it's one of the most beautiful calculations that I know, these quantum fluctuations, these very tiny quantum fluctuations that are always hidden in the microscopic world. They actually grow and become macroscopic in size. And in fact, they have exactly the right characteristics to produce these fluctuations, these temperature fluctuations that we see in the cosmic microwave background. So you can predict the precise details of these temperature fluctuations in the cosmic microwave background and the consequential structure formation later on. So forget about the fact that we're all stardust. We are all stardust, right? The heavy elements are made in stars. But ultimately, in the end, all structure arises from small quantum fluctuations during inflation. So it can also explain that. On top of the fact that the universe is very smooth, the small fluctuations can also be explained by quantum fluctuation. And different models of inflation give different precise predictions for these fluctuations. So we can now distinguish between these different models of inflation, or hope to distinguish between these different models of inflation, by just measuring these temperature fluctuations and all these structures that we see to measure it better and better and better. The hope is that we can then land on a particular model of inflation and prove that this is what actually happened. Okay? But it sounds almost too good to be true. Oh, perhaps it is. The last 5 minutes, I'm going all overboard. So far, so good, right? Yes. Okay. So I told you I need very exotic matter. I need an inflaton field. So might there be an inflaton field, a particle in string theory, that does exactly this job? The good news is string theory has many, 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 many possibilities. Some people say that's bad news. You want to be very unique. But there are many possibilities, and there's no reason to think that you cannot have some inflationary phase in a particular string theory model. But the bad news is, although string theory has been able to produce particle physics models that look relatively okay, it has been unable to produce a controlled example of inflation. Now, some of you might know that string theory predicts what is called a multiverse. All these different universes with all these different properties. Now, maybe that's the way out, because we only need one inflationary universe, right? Then that would be enough. One is enough. But nobody has ever been able to show a fully controlled example of accelerated expansion. Apparently, string theory doesn't like accelerated expansion very much. We lose all control. Now, this brings me to another question. If we confirm inflation, can we then rule out string theory? That might be the best of all worlds, right? So we can rule out string theory if we prove that inflation doesn't fit with string theory. So these are really exciting questions that, of course, I cannot give an answer to, but it's some of the, I think, strongest motivation for the stuff that I do. Okay? I want to connect this explanation for the special properties of our universe to a model that suggests to be the best description of a quantum mechanical gravity theory. So hopefully we can combine these two and use, in some sense, inflation to learn more about that very exotic high-energy theory. The reason this is all connected, and this is also what we think quantum gravity is all about, and which is also certainly true in string theory, is that far from being accidental details, the properties of nature's basic building blocks, including the inflaton, are deeply entwined with the fabric of space and time. So if you know something about the particles that live in our universe, if you know something about inflation, then you also have a chance to know something, to learn something, let me put it this way, about quantum gravity and string theory. That's the hope. That's the hope. Now, how would you do that? I just want to finish, in some sense, with a couple of remarks on how you would actually do that and why it is so difficult. I think you probably heard this before. Some of you might have heard this before. But gravity, actually, this is a very interesting statement, because gravity is the weakest force we know. Of all other forces, gravity is the weakest. That might not be obvious, because we all feel gravity, we don't feel electromagnetism, but that's because gravity is democratic and works in exactly the same direction if you combine a lot of matter. If you look at elementary particles, gravity is by far the weakest force. And there are some reasons to think that this is not just an accident. I don't know what happened. This is not just an accident, but that has to be the case. It's like a necessary condition to make physics work somehow. So gravity is the weakest force, implying its quantum nature is the hardest to test. So basically the fluctuations, quantum fluctuations that are all hidden in the microscopic world, they're deeply connected, they're directly connected to the strength, strength of the force that you're talking about. And because gravity is so weak, you have to go to ridiculously small distance scales to see these fluctuations. So particles at LHC, where we crash particles into each other, is about 10 to the minus 20 meters. But you have to go another 15 orders of magnitude to actually probe the true quantum nature of gravity. So that's a very tall order. Now, the good news is that inflation could have an energy which is as high as the gut scale, which is over here, which is relatively close to the Planck mass, which sets basically the scale of gravity. So inflation, as a very extreme high-energy event, is relatively close to the Planck scale. Not as high as the Planck scale, but relatively close. So that's good news. So maybe if we at some point understand what the actual scale of inflation is, we can get relatively close to the Planck mass and maybe test aspects of quantum gravity. Who knows? So there are two options. You either go to directly get close to the Planck scale. Well, inflation might do that. But you can also indirectly predict. So some consequences of quantum gravity might be indirect and trickle down all the way to very low energies. Okay? And some of the most interesting properties of quantum gravity have to do with holography. And if some of you went to a talk by Erik Verlinde, it has something to do with black hole physics. Black holes have a temperature and somehow can be described by the surface of this horizon. And the surface can be very big and it's still holographic. So there might be some properties of quantum gravity that actually trickle down to very large scales. Now the good news is that not only is inflation very close to the Planck scale, relatively close to the Planck scale, but it also has some holographic properties. If you have an accelerated expansion of space-time, you also live in a space-time with a horizon. Instead, the horizon is not at a particular location where the black hole sits, it's surrounding you. So one of the main motivations for my work is also to see if we can combine these two features, directly and indirectly, test features of quantum gravity by really diving into the physics of inflation and see if there's something that we can in principle, not in practice for now, in principle measure. Okay? Good. That brings me to the end. It's actually perfect. Wow. Brings me to the end. This was lightning fast, as it should for a cosmology talk. There was a lot of ground to cover. I hope I've given you a glimpse of what we know, and especially also what we do not know. We don't know what the model of inflation is, what the theory of inflation is, but we have every reason to think that something like inflation must have happened to explain the special properties of our universe. And the hope is that we will know more and more in the future about this special early phase that our universe brought our universe into existence. And my hope is that at some point, well, first of all, inflation best explains these special properties. I don't know of any other explanation that can do the same thing. And it provides an exciting opportunity to test features of quantum gravity in the future. Maybe it's our only way to test features of quantum gravity. Who knows? So with that, and this very short summary of the history of our universe, let me thank also a bit my sponsors, and especially you for your attention this evening.
Thank you.